Every linear transformation, no matter how complex looking, is an ordered sequence of a few simple moves. Let's take some vectors and transform them with the matrix on the top left. Pay attention to their directions. Some vectors changed directions, some didn't. We call those that didn't eigenvectors. And how much the vectors stretched in their directions, eigenvalues. And here is the interesting part. If a matrix have enough linearly independent eigenvectors, we can use them to form a new basis. And we call the process diagonalization. But there's a catch. It only works for some specific square matrices. Other matrices, even if they are square, simply don't have enough eigenvectors to form a basis. This leaves us with a nagging question. Is there a way to find a useful diagonal matrix of any linear transformation? Yes, there is. This is where singular value decomposition, or SVD, enters the stage. If diagonalization is a specialized tool for a specific class of problems, SVD is the master key. It allows us to take any transformation and break it down into identifiable steps. To understand what SVD is actually doing, let's think about how a linear transformation affects the space it lives in. Imagine a unit circle in a 2D input space. When we apply a linear transformation to this space, that circle usually gets stretched and tilted into an ellipse in the output space. The core insight is this. No matter how distorted that ellipse looks, we can always find a set of perpendicular vectors in our input space, which become the axes of the ellipse after transformation. We describe this process as a sequence of three distinct motions, U, sigma, and V transpose. Going right to left, we begin with V transpose, a rotation in the input space. We rotate our coordinate system so our basis vectors align with the directions that will become the axes of our ellipse. Visually, the unit circle spins but doesn't look any different. Next, sigma scales these vectors. The factors by which we stretch or squish are called the singular values. Now the circle deforms into an ellipse. If a singular value is 0, that entire dimension collapses. The number of non-zero singular values is the rank of the matrix. Finally, U rotates the scaled vectors into their final orientation in the output space. Notice that SVD allows the input basis and output basis to be different. As long as both are orthonormal, the vectors form a basis. They are perpendicular, and their lengths are exactly 1 unit. This flexibility is exactly why SVD works for every single matrix in existence. As a side note, to find the U and V matrices, we look at two special products. A transpose A and A transpose. Why them specifically? Because they're always symmetric. A symmetric matrix mirrors its entries across the diagonal, and symmetric matrices always diagonalize with orthogonal eigenvectors, meaning perpendicular. That perpendicularity is exactly what gives us the V and U matrices in SVD. However, finding these eigenvalues requires solving a polynomial equation of degree n. For n of 5 or higher, there is no closed-form solution. So in practice, SVD uses an iterative algorithm that converges toward the answer rather than computing it exactly. There is also a deeper problem. Computing products like this on a computer is numerically unstable. Take a matrix with a very large entry and a small one. When you compute products, the large entry gets squared to enormous value. At that scale, floating point arithmetic simply cannot represent the small entry accurately anymore, and all precision is lost. This is why modern SVD implementations work directly on the matrix A, never forming the product at all. It is natural to wonder how this relates to the diagonalization process.
Is SVD simply an improved version, a mathematical update that we all need? Unfortunately, number.
You can think of diagonalization as a search for fixed directions. We want to find a basis where the input and output are the same such that the transformation is just a scalar multiple. The problem is that for many transformations, such fixed directions don't exist in a way that captures the whole transformation. A rotation matrix, for instance, has no real eigenvectors because every vector is moved off its span. However, SVD doesn't care if the vectors stay on their span. It only cares that we can find a perpendicular set of vectors that ends up as another perpendicular set of vectors, just potentially rotated and scaled. There is a beautiful bridge between the two. If you have a symmetric matrix, one that equals its own transpose, SVD and diagonalization become the same thing. In that specific case, the singular values are simply the absolute values of the eigenvalues. And the input and output rotations happen to be the same, so U and V collapse into one. Visually, the two decompositions look the same, both rows collapse to the same formula. In every other case, there is a distinction to draw. If you are analyzing a process that repeats, like interest rates or a Markov chain, follow the eigenvectors. They tell you where the system will end up after many, many steps. If you are analyzing a single snapshot of data or a physical deformation, follow the singular vectors. They tell you how the shape is distorted, and where the most significant information is stored, the direction that is stretched the most. And it is helpful to know that singular vectors always exist, for every single matrix, without exception. Because SVD isolates the most important directions of a transformation, it acts as a perfect filter for information. This is the secret behind many technologies we use daily. Think of a high-resolution photograph. To a computer, that's just a massive matrix of color values. By performing an SVD, we isolate the largest singular values, which capture the primary structure of the image. If we keep only the top k singular values and throw away the rest, we reconstruct an image that looks nearly identical to the original, but stores only a fraction of the data. We're essentially telling the computer, ignore the noise and tiny details. Just give me the primary structural components. The big shapes, the lighting, the contrasting lines. Beyond images, SVD is the engine behind Principal Component Analysis, or PCA, one of the most widely used tools in data science. Imagine a dataset of hundreds of people, each described by dozens of measurements. That's a cloud of points in a very high-dimensional space. Impossible to visualize. PCA uses SVD to find the directions along which your data varies the most. The axes of greatest spread. Those principal components are exactly the axes of the ellipse that your data cloudform's SVD finds them the same way it always does. By identifying the directions that carry the most information. By projecting everything onto just the top 2 or 3 directions. You can collapse that high-dimensional cloud into something you can plot and reason about, while preserving as much structure as possible. The dimensions it keeps are those with the largest singular values. The ones it discards are the noise. Perhaps the most counterintuitive application is in human language itself, fabulously called latent semantic analysis. What SVD tries to do here is uncover the hidden relationships between words and the concepts they represent. In linguistics, we often deal with a term document matrix where every row is a unique word. Every column is a specific document. and each entry records how often that word appears. The problem with these matrices is that they are incredibly messy. Language is full of synonyms, different words with the same meaning, and polysemy, the same word with different meanings, creating a noisy space where the computer sees two documents as unrelated just because they use different vocabulary to describe the same topic. By applying SVD to this matrix, we perform a sort of linguistic compression. Instead of seeing words as isolated units, it groups them into clusters based on where they appear. Then, by keeping only the top k singular values, we effectively smooth the data. This ignores the minor, accidental word choices of an author and focuses on the primary semantic structure. If marathon and sprint frequently appear in the same documents, SVD maps them to the same underlying concept of running. We can now compare documents not by whether they share the exact same words, but by whether they share the same conceptual space. This allows a search engine to understand that a query for feline should return documents about cats, even if the word feline never appears in the text. It's a profound thought. The same geometric principle that describes how a circle turns into an ellipse is the same principle that allows a computer to understand the underlying structure of human preferences, or the essence of a digital photograph. SVD transforms a chaotic, high-dimensional world into a structured, geometric landscape where meaning is defined by semantic proximity, not just how they are presented.